Hey guys, Mr. Backerberg here. In this video we're going to take a look at upper and lower bounds. So as we're looking for upper or lower bounds of the real zeros of a polynomial function, so let's say that f is a polynomial function with degree of 1 or higher, and we've got a positive leading coefficient. And say we're trying to do some synthetic division to find rational zeros. So we're dividing by x minus k using that synthetic division. If our k value is greater than or equal to 0, and every number that we get in the last line of our synthetic division is non-negative, so meaning either positive or 0, then that k value that we were dividing by is an upper bound for the real zeros of our function f, meaning that our function won't have any zeros that are higher than that k value. But if that k value is negative, and all of the numbers in the last line alternate between being non-negative and non-positive, then our k value is a lower bound, meaning that we're not going to have any zeros that are lower than that specific k value. So the first thing we're going to do is look at establishing some bounds for the real zeros of a polynomial function. So we're looking at the function f of x equals 2x to the fourth minus 7x cubed minus 8x squared plus 14x plus 8, and we're going to prove that all of the real zeros of that function lie on the interval between -2 and 5. And we're going to do this by using synthetic division. So I'm going to start by setting up my synthetic division bracket, and I'm going to put all of those coefficients on the inside of my synthetic division bracket there. And the first thing that I want to prove is that 5 is an upper bound for the real zeros of this function. And in order to prove that 5 is an upper bound, then I want to show that as I do my synthetic division, the numbers that I get in my last line here, I want them to all be non-negative. So either positive numbers or 0. So I'm going to start doing my synthetic division. So I drop down the 2. 5 times 2 is 10. I take the -7 plus 10 to get 3. 3 times 5 is 15. If I add up the -8 and the 15, I'll get 7. 5 times 7 is 35. When I take 14 plus 35, I'm going to get 49. And 49 times 5 is 245. And when I add that together with my 8, I get 253. So as I look at all of the numbers down here, I can see that all of these numbers are non-negative, therefore proving that 5 is an upper bound. Now the other thing that I want to prove is that -2 is the lower bound. So I'm going to do a different round of synthetic division, but again I'm going to fill in all of those coefficients from my polynomial function. And I'm going to synthetically divide by -2. But in order to prove that this is a lower bound, then these numbers that I get in my last line here, I want them to alternate between being non-negative and non-positive. So I'm going to start by dropping down the 2. And when I do that, I'll take the 2 times the -2 to get -4. Add the -7 to the -4 to get -11. -2 times -11 is positive 22. And when I add that up with the -8, I get 14. 14 times -2 is -28, and when I add that together with that 14, then I'm going to get -14. -14 times -2 is positive 28, and if I add that to my 8 on the end, then I'm going to get 36. So I can see that all of my numbers in my last line are alternating between being non-negative and non-positive, meaning that that -2 is in fact a lower bound. Now this didn't help me find any zeros because I didn't get 0 as the remainder when I was doing this synthetic division. But what it did prove is that all of the real zeros that we can find have to be between -2 and positive 5. So that really helps us narrow down all of the values that we could have as zeros for this polynomial function. So now let's look at that same f of x function, but let's work on finding its real zeros. And I'm going to start by using the rational zero theorem to help me find potential real zeros. So I'm going to think about making a list of p over r fractions, and those p values come from the factors of the constant term on the end. So we could have plus and minus 1 or plus and minus 8. We could have plus and minus 2 along with plus and minus 4. So we have quite a few p values in there. Now as far as the r values on bottom, I want to focus on the leading coefficient there, which is a 2. So I could have plus or minus 1 and plus or minus 2. Now if I think about making my list of potential rational zeros, I'm going to start by taking all of these p values and putting them over 1. So 1 divided by 1 is 1, but again we're going to keep the plus and minus on there. 2 divided by 1 is 2 with the plus and minus. 4 divided by 1 is 4 with the plus and the minus. And 8 divided by 1 is 8, but again keeping the plus and the minus on there. Now I'm also going to take these p values and put them all over 2. So if I take the 1 over the 2, I'm going to get 1/2 with the plus and minus on there. Now 2 divided by 2 is 1, and I've already got 1 on my list. 4 divided by 2 is 2, and I've already got 2 on my list. 8 divided by 2 is 4, and 4 is already on my list. So it's not necessary to write down those repeated values. Now, in the last example, we just proved that all of our real zeros need to fall on the interval from -2 to +5. So that's going to help me eliminate some of these values. So as I look at the plus and minus 1, both of those values are between -2 and 5. So those are still potential zeros. -2 and +2 are on the interval from -2 to 5, but I already tried -2. I did synthetic division with -2 and I got a non-zero remainder. So that means that -2 won't be a zero, but +2 is a potential zero. Now -4 does not fall in this interval, so I'm not going to put it on my list, but +4 does fall on the interval, so that one is a possible zero. +8 and -8 don't fall on the interval from -2 to 5, so that's not a possibility. 1/2 and -1/2 do fall in this interval, so those are possibilities as well. So we've narrowed down that list quite a bit by finding these upper and lower bound values for my potential zeros. So I'm going to look at doing my synthetic division. So I'm going to set up my synthetic division bracket with all of my coefficients on the inside of that bracket. And I'm going to guess a number off of my newly narrowed down list. And I'm going to guess 4. Now I'm going to drop down the 2. 2 times 4 is 8. -7 plus 8 is 1. 1 times 4 is 4. -8 plus 4 is -4. 4 times -4 is -16. -16 plus 14 is -2. And 4 times -2 is -8. So we get a 0 remainder in there, which proves that x equals 4 is a 0 of my polynomial. And because x equals 4 is a 0, then x minus 4 is a factor. Now I'm going to continue on with my synthetic division. And this time I'm going to guess -1/2. I'm going to drop down the 2. -1/2 times 2 is -1. If I add these together, I'm going to get 0. -1/2 times 0 is 0. Add up the -4 with the 0, I get -4. -1/2 times -4 is +2. So I get a 0 remainder in there, which proves that x equals -1/2 is a 0 of my polynomial. And because x equals -1/2 is a 0, if I multiply the 2 over and then add the 1, that would mean that 2x plus 1 is a factor. Now, taking a look at what we've got left over, I'm actually going to put some x's back in here. We started with a quartic function, but ran 2 rounds of synthetic division. So as I put my variables back in there, I need to drop the power by 2. So this 2 is really on an x squared. This 0 would be on a plane x, and this -4 would be a constant term on the back end. So this is going to be my remaining factor of my polynomial. So 2x squared minus 4. And I can actually use that to help me find the remaining zeros of my function. Now they're not going to be rational zeros, they're going to end up being irrational. But if I take that factor and set it equal to 0, so 2x squared minus 4 equals 0, I can add that 4 over to the other side, so I get 2x squared equals 4. Dividing both sides by 2, I'll get x squared equals 2. And then to get rid of that squared power, we're going to square root both sides. So I get x equals, now on the right hand side, when I square root that 2, I have to remember to put the plus and the minus in front of it. And 2 is not nicely square rootable, so I'm just going to leave it as the square root of 2. So my last zeros are at x equals positive square root of 2, and also at x equals negative square root of 2. That's going to be it for this video. Thanks for watching.